quantities in a reaction or stoichiometry. So stoichiometry is basically the study where we try to understand a quantitative relationship between reactants and products. So for example, if this is a chemical reaction where iron is reacting with oxygen to give us iron oxide, and I ask you how many moles of iron oxide can be formed from 6 moles of oxygen. So we have 6.0 moles of this, and the question is asking how many moles of the other compound can be made. Or if it could ask, if I have 6 moles of this, how many moles of iron would be needed? So basically this is a very important concept that is needed if you're trying to do a chemical reaction. So it tells us how much raw material is needed, how much product can you expect from a chemical reaction. So that is why stoichiometry, or understanding the chemical quantities in a reaction, becomes so crucial. Now the question is, how exactly can we do this? So to understand this, let's try and take an example of basically something from our kitchen. So a recipe for a grilled cheese sandwich essentially is, for every sandwich that we want to make, we need 2 slices of bread and a slice of cheese. So if I tell you you have 10 slices of bread, you'll say you'll get around 5 sandwiches from it. How do we know that? The recipe tells us for one sandwich I need 2 slices, which means if I have 10 slices of bread, that would give me 5 sandwiches. And that's exactly what we do in chemistry as well. Chemistry, the chemical reaction is basically the recipe. So if you have 2 slices of bread, if I write this recipe in form of a chemical reaction, I would write it like this: 2 bread slices, 1 cheese slice will give me 1 sandwich. So these 2 are my reactants and this is my product. And what you see in front is how many of each of these materials do you need, and that is basically moles of that reactant. So if I have 2 moles of this, meaning if I have 2 slices of bread, I get 1 sandwich. Similarly, if I have 2 moles of the bread slices, I'll get 1 mole of sandwich. Similarly, if I have 1 for every 1 slice of cheese, I'll get 1 mole of sandwich. So in this way, you can relate reactant with another reactant. You can figure out, if I have these many sandwich slices, how many cheese slices do I need? Or you can relate your reactant with the product. Okay. Now this is something that you are able to do in your head, right? You don't need a calculator for it, or you don't really have to think too much about it. But what if I give you numbers in chemistry? So one way to do this is, you need a conversion factor to be able to do this. So what are my conversion factors? The recipe right here gives me my conversion factors, meaning if I have 2 slices of bread, that would produce 1 sandwich. And this is my conversion factor between my reactant and product. What are these numbers? These numbers are again the moles of reactant and product. And now if I tell you you have 10 slices of bread, and we are trying to figure out how many sandwiches, this is my conversion factor. I have slices of bread up here. This is going back to dimensional analysis. So I'll put slices of bread in the bottom, so that whatever is your starting unit, the unit that goes right across is also the same unit. So how many? 2, which is coming from this conversion factor, and whatever is the other factor goes on top. 1 sandwich. Slices gone. Your final answer is in sandwich, which means 10 multiplied by 1 divided by 2 gives you 5 sandwiches. And that's exactly what we did when you try to do this in your head. And that's the same thing, same concept that we apply in chemistry. So let's go back to our actual question, which was, if we have this particular reaction and you have 6.0 moles of this, how many moles of iron oxide can you make? Okay, important thing is, based on this, you can relate any reactant or product to each other. So for example, if you have 4 moles of iron, you would need, for every 4 moles of iron, you would need 3 moles of oxygen, O2. For every 4 moles of iron, you would make 2 moles of iron oxide. So basically, your chemical reaction, you can read it in this format. 4 basically means 4 moles of iron, 3 moles of O2, 2 moles of iron oxide. So this is your chemical reaction now. And it tells you how each quantity is related to each other. So if you want to relate iron to oxygen, you can do that. Iron to iron oxide, we can do that. Oxygen to iron oxide, we can do that. Okay? So if my question was, I have 6 moles of oxygen, I'll put my starting is 6 moles of O2. What is my, what do I need? I need moles of iron oxide. So I need a relationship between these two quantities. And my relationship would be 3 moles of O2 will produce 2 moles of iron oxide. So again, whatever is your starting unit, which is in this case is moles of O2, will go right across. So moles of O2 will go in the bottom. How many? From my conversion factor, 3 moles of O2. And whatever is the other unit goes on top, 2 moles of iron oxide. So now if you cancel moles of O2 with moles of O2, you're left with moles of iron oxide. Okay, which would be 4.06 multiplied by 2 divided by 3. Important thing here to remember is whenever you're making this relationship, these numbers are only, the unit that you can apply with these numbers is only moles. Okay, so only way to relate these reactants and products to each other is via moles. So if you have 4 moles of iron, you'll get 3 moles of oxygen. You cannot use any other unit. This relationship will not work with any other unit. You cannot use grams, you cannot use number of atoms, molecules. Only unit that can be applied is moles. And next important thing is that this chemical reaction has to always be a balanced chemical reaction. Chemical equation, balanced chemical equation. So that is why these conversion factors are also called as mole to mole ratio conversion factors, because these are like ratios, 4:3, 4:2. So these are called as mole to mole ratios that can be used for going from amount of substance 1 to amount of substance 2. Okay, so now we already saw previously that if I start with moles of one substance, moles of A, it can be related to grams of A or mass of A. How? Using molar mass, meaning 1 mole of a substance is equal to molar mass of that substance in grams. Similarly, moles of A can be related to units, number of units, which is number of particles, using Avogadro number. Okay? 1 mole is equal to 6.022 times 10 raised to power 23. The important thing is, if you want to go from moles of a substance A to moles of substance B, the only way you can do that is through moles and moles. You cannot go directly from grams of A to grams of B. You cannot do ml of A to ml of B. Only way you can go from amount of A to amount of B is through moles. So just important thing to remember is moles. And what would be your conversion factor here? The relationship is going to be mole to mole ratio that you get from the balanced equation that we just saw. Okay, so a balanced chemical equation will give you the relationship to go from moles of A to moles of B. And then once you know moles of B, if the question is asking to convert it to grams, you can convert it to grams of B. How? Using molar mass. 1 mole is molar mass again. If the question is asking number of particles, units, atoms, then you use Avogadro number. So if you are going from amount of substance A to substance B, there's only one relationship that you can use, which is mole to mole. And after that, you can convert to whatever the question is asking. Meaning, if the question says it gives you grams of A and it is asking you grams of B, you cannot directly go from this to this because there is no relationship. Only way you will be able to do this is if you start from mass of A, convert that to moles of A, then convert moles of A to moles of B, and then you can go to mass of B. So you will have to have multiple steps in order to get to your final answer. So now for this, remember this map because this is going to solve every single question now. moving forward. Okay, what we saw previously was basically 1/2 of this when we were only dealing with A as a substance. Now we have added a second substance, so that basically adds this particular important relationship, which is mole to mole in the middle. Moving forward, for every single question we will be using this map. We will be making map using this particular sheet as our cheat sheet. Moles to moles of another substance is mole ratio, and these are the relationships to go between grams, moles, and number of particles. Okay, so let's try one question. How many grams of oxygen are needed to produce 45.8 grams of iron oxide in the following reaction? So question is asking how many grams of oxygen are needed to produce 45.8 grams of Fe2O3. So if I want to make 45.8 grams of this, how many grams of oxygen should I use for that? Which means I need to go from amount of substance A to amount of substance B. The only relationship that can help me do that is mole to mole. But moles are not given to me, which means we will have to make a stop in the middle for moles. Okay, so let's try and make our map. Let's start with what's given to us on the left. What's given to me is grams of Fe2O3. And what the question wants me to do is to figure out grams of oxygen that are needed to make this. Now there is no direct relationship to go from grams of substance A to grams of substance B. If your substance changes, you do not have a direct relationship. The only way to do that is from mole to mole, which means if I want to go from amount of this to amount of this, I need to know moles of each of these quantities. So first thing I'll have to do is I'll have to figure out moles of this. How? Like we saw in our previous sheet, I'll have to convert moles of Fe2O3, grams of Fe2O3 into moles of Fe2O3. And what is my relationship going to be here? It will be molar mass. Okay. Next, I can convert moles of Fe2O3 into moles of O2, because the only way I can go from one substance to another is via moles, and my relationship will be from this chemical equation. And the last step would be moles of oxygen to moles of grams of oxygen, which I know can be done through molar mass again. So what we'll have to figure out molar mass for each of these, both of these quantities. So let's find molar mass of Fe2O3. Fe2O3 has 2 iron atoms, 3 oxygen atoms. So that would be 2 iron, 3 oxygen. So let's add the masses. 2 times iron from periodic table is 55.85 grams. Because I have 2, I double it. Plus 3 oxygen, 3 times 16.00. When you solve for this, it will give you a molar mass of 159.70 grams, which means my first relationship is 1 mole of Fe2O3 is 159.70 grams. Now, important thing to remember here is, even though if you look in the equation, I have 2 moles of Fe2O3, but when I write molar mass, that should always be for 1 mole. Remember, the definition of molar mass is mass of 1 mole of a substance. So even though this is a 2 here, for the molar mass, your number will always be 1. Next is molar mass, mole to mole ratio between Fe2O3 and oxygen. This is where I will use this stoichiometric coefficient. Okay, so remember these numbers in front, they are never used except when you're going from moles to moles. Okay, so what is my relationship here? It is going to be for every 3 moles of O2, we get 2 moles of Fe2O3. Next, I go from moles of oxygen to grams of oxygen. For this, again, I need molar mass. So we'll find molar mass of O2, that's O2. So 2 oxygen atoms, so 2 times 16.00 will give you 32.00 grams, which means 1 mole of O2. Again, this is 1. Why? Because we are talking about molar mass. Molar mass is always for 1 mole. 32 0.00 grams. Now you have your steps and you have a conversion factor relating them. Okay, so we'll start with the first step, which was 45.8 grams of Fe2O3. I will multiply it with a factor that comes from this relationship. One of these quantities goes on the bottom, one goes on top. How do I decide? Depending on my starting unit. My starting unit is grams, which means I should have grams of Fe2O3 in the bottom. How many grams? Right here, 159.70 grams, 1 mole of Fe2O3. Gram, gram, gone. Make sure you're cancelling the unit and the substance. So you can only cancel the same substance. What I have as a unit is moles of Fe2O3, which is right here, which means I've reached my second step. I need to go from moles of this to moles of oxygen, so I multiply with another factor that comes from this second conversion factor. My starting unit is moles of Fe2O3 right here. My starting is mole of Fe2O3. So what goes in the bottom should be mole of Fe2O3. How many mole of Fe2O3 here? Based on my relationship, 2. So I'll put a 2 right here, and 3 moles of O2 goes on top. This and this cancels. I'm left with moles of O2, which is next step. I'm here now. I need to convert this. How? Using this conversion factor. So again, I multiply with a factor coming from these two. 3 moles of O2 here, so mole of O2 goes in the bottom. How many? Based on this, it's 1. So 1 mole of O2, 32.00 grams of O2. Mole go on, you're left with grams of oxygen. So that's your final answer. Now you just plug all these numbers into calculator. How would you plug? 45.8 multiply by 1, multiply by 3, multiply by 32. Plug all the ones on top in the numerator in one go, then divide it by 159.70, get your answer. Divided by 2, get your answer. Divided by 1, it should give you the same answer. So your final answer that I see is 13.8 grams of oxygen. This was 3 significant figures. This is 3 significant figures. Okay, let's move on and try one more example of similar pattern. Determine the mass in grams of ammonia that can be produced from 32 grams of nitrogen. So the question says you have 32 grams of nitrogen and it's asking how many grams of ammonia can you make. Again, if I want to go from substance to second substance, I need mole to mole. So let's write down what's given to me is grams of nitrogen. The question wants me to find grams of ammonia. Again, in order to go between the two substances, I need to make a stop where I have to find moles of nitrogen. So I'll have to convert grams of nitrogen to moles of nitrogen. Then I can convert moles of nitrogen to moles of ammonia. And once I have moles of ammonia, I can convert it to grams of ammonia. What is the relationship between grams and moles of one same substance? It is the molar mass. So I need to find molar mass of nitrogen, which would be 1 mole of nitrogen weighs how much? It is nitrogen. So you have 2 atoms of nitrogen. Each is 14.01 from periodic table. Total is 28.02 grams, meaning 1 mole weighs 28.02 grams. Next, I need mole to mole ratio. I need to go from moles of this to moles of this. What is the ratio? Right here, no number is written, which means that's 1, and this is 2. So for every 1 mole of nitrogen, we make 2 moles of ammonia. So I have a conversion factor here. Next is I need to go from moles of ammonia to grams of ammonia. What would be my conversion factor? Remember, moles to grams is always molar mass. So my conversion factor here would be 1 mole of ammonia. Why 1? Again, molar mass is always for 1 mole. Find the molar mass of ammonia. Nitrogen, 1 nitrogen, so 14.01. For nitrogen plus 3 hydrogen, so 1.008. When you plug this into calculator, it gives you 17.034 grams. So 1 mole is 17.034 grams of ammonia. And that's it. I have my solution map made. Now we start with grams of nitrogen, 32 grams of N2. Multiply it with one fraction that comes from my first conversion factor. Starting is grams of nitrogen, so I should put grams of nitrogen here. How many? 28.02, and 1 mole of nitrogen on top. Gram gone. Multiply it with the next factor that comes from the next conversion factor. Because my starting unit now is moles of nitrogen, I'll put moles of nitrogen in the bottom. How many? 1. And 2 mole of ammonia goes on top. Mole of nitrogen gone. Now my answer is in moles of ammonia, which means I'm right here in my next step. So I move on and continue with the next conversion factor, which is right here. Moles of ammonia is my starting unit right here, which means moles of ammonia should go in the bottom. How many? Based on this, it's 1, so 1. And the next is 17.034 grams of ammonia on top. Mole gone. Your final unit is grams of ammonia, NH3. Plug this into your calculator and you should get 39 or 38.907 grams from your calculator. Now the starting number, this is 2 sig figs, this is 1, 2, 3, 4 sig figs. This we don't care about because it's just numbers. It's a counted value. This is 1, 2, 3, 4, 5 sig figs. Least of them all is 2. So my number should end 1, 2 at 8. The following digit is 9. So this would become 39 grams of ammonia. That's your final answer. Okay. Those were some of the examples. If one amount of one of the reactant is given, then the question is asking how much product, or vice versa. But now let's look at another concept. If I ask you this question, go back to our sandwiches. If I ask you how many cheese sandwiches can be made if you have 20 bread slices, so have 20 of these and 4 cheese slices. Okay, so what would be your answer? If you have 20 bread and 4 cheese, how many sandwiches can you make? Somebody would say 4 sandwiches. How do you know this? We know that from 20 slices of bread, ideally, how many sandwiches can you make? From 20 slices of bread, we can make 10 sandwiches. And from 4 cheese slices, you can make 4 sandwiches. But you will not be able to use all your 20 slices of bread. Why? Because once you make your 4 sandwiches, we do not have any more cheese left. Okay, so no cheese after 4 sandwich, which means once the 4 sandwiches are done, you have all your cheese is gone. I have some bread left, which means just with bread, I'm not able to make a sandwich because one of my ingredients is over. So this is the one ingredient that is controlling how much product you can make is called as the limiting reactant. The reactant right here that is controlling how much product can be made, that is controlling what is the amount of product made, is called as limiting reactant because it is limiting the amount of product being made. So this is the reactant that finishes faster. Okay, how would you be able to do this? The reactant that finishes faster is called the limiting reactant. The reactant that is present in extra amount, which would be left over, is called as excess reactant. Okay, so once your 4 sandwiches are made, you would use, basically for 4 sandwiches that you made, you would use 8 slices of bread, and the rest, all 12 slices, will be excess reactant that would be left behind. Now, how do you usually would do this? If the same question is given to you with actual chemical reaction, you would convert. First, we converted my bread slices into my product. I found I can make 10 sandwiches from here. Then I converted my cheese into product, which told me you can make 4 sandwiches. Whichever reactant gives me less product is my limiting reactant. So first way, the only way you're going to solve for questions of limiting reactant is you will first convert your first reactant into product, figure out how much product it gives you. You will do the same thing for second, and whoever gives you lesser product, this can give me 10, this can give me 4. Lesser is 4, which means my limiting reactant is the cheese. That's how we figure out who is your limiting reactant and how much product you can get. So from here, I can say only amount of sandwich that I can make is 4. So there is no shortcut to this. If the question tells you you have 2 reactants and it gives you amount of each and it is asking you how much product can be made, remember you have to convert both of your reactants into products and figure out how much product you make from each. Whoever gives you less, that is limiting reactant, and whatever you make, whichever is the lesser value made, that is your amount of product made from that chemical reaction. And the amount of product actually made from the chemical reaction is called as the yield of the reaction. In chemistry, the amount of product made from a reaction is called as yield of reaction. So this is how much product you can make from this reaction. Now this is in theory. So this is called as the theoretical yield of the product, meaning theoretical means in theory. This is based on calculation. So if you give me 20 slices of bread and 4 cheese slices, I should give you 4 sandwiches. But let's say I burned maybe 2 sandwiches out of it. When I was cooking, I should give you 4. But what did I do? I burned 2 of those. So how much product did I actually made? That would be called as your actual yield. Actual yield is when somebody actually did the experiment, how much did they actually end up producing, how much product was made in the actual experimental condition. This is called as the actual yield or experimental yield, which is how much you ended up making. So I burned 2, which means how much did I actually made? 2 sandwiches. Now if I want to see what percentage of sandwiches did I end up making, that term in chemistry is called as the percent yield. Percent yield has a formula which is called actual yield over theoretical yield times 100. Okay, so this is the formula for percent yield. Actual yield over theoretical yield times 100. What is actual yield? It is the yield, actual or experimental yield is the yield that was actually made, amount of product that was actually made when somebody did the experiment. Theoretical yield is the yield that was calculated based on numbers. How? Stoichiometric numbers. Okay. So this is the same concept. We'll try to do questions based on these concepts. The definitions are also listed here. A limiting reactant in a chemical reaction is the substance that is used up first and it limits the amount of product that can form. The reactant that does not completely react and is left over at the end of the reaction is called the excess reactant, meaning you have more of it, but you're less on the other reactant. So the ingredient which is less is the limiting reactant. Ingredient which is present in more is the excess reactant. Theoretical yield is the maximum amount of product that can be calculated using the balanced equation. So this is the amount of product that can be made from the limiting reactant. Actual yield or experimental yield is the amount of product that was actually obtained when the experiment was done. So this number will always be given to you in question. You cannot figure that out because you would not know how much product was produced from the experiment. If you're doing calculation, only number you can figure out is theoretical yield. And percent yield is the ratio of actual yield and theoretical yield, which is calculated using this formula. Okay, so now let's try some questions based on this concept. If 3.00 moles of carbon monoxide, so this is carbon monoxide, 3.00 moles of carbon monoxide and 5.00 moles of hydrogen. So I have 5.00 moles of hydrogen are the initial reactants. How many moles of methanol, which is CH3OH, can be produced? Question is asking how many moles of this can be produced and what is the limiting reactant. So it has two parts to it. It says I have 3 moles of this, 5 moles of this. How much of this will I make? Now this is a question of limiting reactant. How do you know? Whenever amount of two reactant is given and the question is asking how much product will be made, the only way to do these questions is you have to convert first reactant to product, you have to convert second reactant into product and figure out who gives you lesser amount. Okay, you cannot make the assumptions that because you are starting with lesser amount of carbon monoxide, it is your limiting reactant. We cannot make that assumption. We have to solve for the amount of product made first. Okay, so how would we do that? You already know now that we can convert or we can go from amount of one substance to other using mole to mole ratio. So that's the same concept we will use. First, let's start with carbon monoxide to CH3OH. How many? What's given to me is moles of CH3OH, sorry, moles of CO, and the question is asking how many moles of CH3OH. What is my relationship between these? Because these are both moles, no number is written here, which means this is 1. So for every 1 mole of CO, I make 1 mole of CH3OH. So for 1 mole of this, you make 1 mole of this, meaning I start with 3.00 moles of CO, multiply it with my conversion factor that comes from here, moles of CO. So mole of CO goes in the bottom, 1 mole of CH3OH. What's left is 3.00 moles of methanol. So this is how much we finally end up making. Similarly, we go from hydrogen to this. Moles of hydrogen is given. Question is asking to find moles of CH3OH. My conversion factor is in the relationship right here. 2 moles of hydrogen, 1 mole of CH3OH. So I'll start with this, which is 5.00 moles of this, multiply it with a factor, mole of hydrogen here, moles of hydrogen, multiply it with this, mole of hydrogen goes in the bottom. How many? Oh, right here, 2 moles of hydrogen, 2 and 1 mole of CH3OH. Mole of H2 go on. I'm left with moles of CH3OH. How many? 2.5. So now if I start with carbon monoxide, it will give me 3 moles of methanol. But if I start with 5 moles of hydrogen, it will only give me 2.5 moles of methanol, meaning once I make 2.5 moles of this, my reaction is done. I don't have any more hydrogen left. So this right here is how much maximum how much product I can make. So the answer to how many moles of methanol can be produced is 2.5 moles of, oh my bad, sorry, 2.5 moles. So how much product can you make? This is your final answer, 2.5 moles of methanol can be made. Whoever gives you lesser quantity. And what is your limiting reactant? Hydrogen is my limiting reactant. This is the reactant. This is the product that is made. So who is controlling how much product can be made is hydrogen. Why? Because it finishes faster. Okay. Let's try one more question. This was directly easy from moles to moles. Now remember the map that we just saw. We can go from grams to moles. We can do this from number of atoms as well. Important thing is, as long as you understand that solution map. Okay. Let's try another question. Silicon carbide is a ceramic material that tolerates extreme temperatures and is used as an abrasive and in the brake disc of sports cars. How many grams of carbon monoxide are formed from 70.0 grams of SiO2? So question is asking how many grams of carbon monoxide will be formed from 70.0 grams of SiO2 and 50.0 grams of carbon. So meaning it is giving you two ingredients and it's asking you how much product will you make. So first thing, whenever two ingredients or two reactants are given to you, the only way to do this is you have to convert carbon to carbon monoxide, SiO2 to carbon monoxide, and figure out of these two who gives you lesser product. Okay, so how would we do this? Let's try that out. So if I need to find this, which means if I want to go from grams of SiO2, or let's start with carbon. If I want to go from grams of carbon to grams of carbon monoxide, grams of carbon to grams of carbon monoxide, what I need in the middle is I have to convert grams of carbon to moles of carbon. Then I need to convert moles of carbon to moles of carbon monoxide, and then I can convert moles of carbon monoxide to grams. How do we go from between grams and moles here? 1 mole of carbon is going to be 12.01 grams of carbon. How? Molar mass from periodic table. 1 mole of carbon to carbon monoxide is right here. For every 3 moles of carbon, we can make 2 moles of carbon monoxide. So for every 3 moles of carbon, I get 2 moles of carbon monoxide. Next, I go from moles of carbon monoxide to grams. For that, I need to find molar mass of this. 1 carbon is 12.01 plus 16.00 for 1 oxygen. Total is 28.01 grams. Which means 1 mole of carbon monoxide is 28.01 grams. Now I have my map completed. I start with grams of carbon, which is right here. How many? 50. So 50.0 grams of carbon. Multiply it with a factor. Because my starting is grams, I put grams in the bottom. How many? 12.01 right here. And 1 mole of carbon goes on top. Gram carbon go on. Now my starting unit is moles of carbon. So moles of carbon should go in the bottom. How many? 3. 2 moles of carbon monoxide goes on top. Mole of carbon gone. Now I multiply with another factor coming from this last conversion factor. Because my starting is mole of CO goes in the bottom, and grams of CO, which is right here, goes on top. How many moles of CO? 1, 28.01 mole carbon gone. Left is grams of CO, which if you plug it into your calculator will give you 77.7 grams of CO. So you get 77.7 grams from 50 grams of carbon. Now I have to do the exact same thing for SiO2. So only difference is, instead of writing it out, instead of grams of carbon, I'll start with grams of SiO2 and then moles of SiO2. So I'll start with grams of SiO2, convert it to mole of SiO2, then mole of SiO2 to mole of CO, and then mole of CO2, grams of CO. For this I need molar mass. 1 SI. SI weighs from periodic table 1 SI, so 28.09 plus 2 oxygen, so 2 times 16.00. If you add it all up, it gives you 60.09 grams, which means 1 mole of SiO2 is 60 60.09 grams. Now mole to mole is right here. For every 1 mole of SiO2 I make 2 moles of CO. Okay, right here. So 1 mole SiO2, 2 mole CO. Now I go from mole of CO to grams. Again, we just figured out the molar mass earlier. So 1 mole CO, 28.01 grams of CO. Now you can start with what's given. 70.0 grams SiO2 multiply 60.09 grams SiO2, 1 mole SiO2, gram gone. Multiply with next factor, 1 mole SiO2, 2 mole CO, mole gone. Multiply with the next, 1 mole CO, 28.01 grams CO, mole gone. What I have is, when you plug this into calculator, gives you 65.3 grams of CO. So you get 77.7 grams from carbon, 65.03 grams from CO. Who is lesser? This is lesser, which means what is your final answer? This is my final answer. How much carbon monoxide can you produce? You can finally produce 65.3 grams of carbon monoxide. That's my final answer. Who is my limiting reactant? SiO2 is my limiting reactant. This is the only way to solve the questions about limiting reactant. You start from one reactant, convert it into product. Second reactant, convert it into product. Whoever gives you lesser amount, that is your amount of product made. Okay. More questions, and those would be the last questions. On a space shuttle, LiOH is used to absorb exhaled carbon dioxide from breathing air to form LiHCO3. All that information we don't care about, we just care about the chemical reaction. What is the percent yield of the reaction if 50 grams of LiOH gives 72.8 grams of LiHCO3? So what is given to us in question is that you have 50 grams of LiOH. It is asking if this gives you 72.8 grams of LiHCO3, what is the percent yield? Now remember, what is percent yield? Percent yield is actual yield over theoretical yield times 100. Actual yield is how much was actually made when the experiment was done. So the question tells you that 72.8 grams was made when you started with 50 grams of this, which means this is my actual yield. What is missing is the theoretical yield. So the question is asking how much is the theoretical. So we'll have to first figure out how much is the theoretical yield, plug it into this formula, and then you can solve for percent yield. How do I get theoretical yield? 50 grams of this, how much of this would have been made in theory? So you already know, you will convert this grams into moles of LiOH. Then you will convert moles of LiOH into moles of LiHCO3. And then you can convert moles of LiHCO3 into grams of LiH. CO3. The conversion factor here is molar mass. 1 mole of LiOH is, if you calculate it, it would be 23.95 grams. How? You simply add 1 lithium, 1 oxygen, 1 hydrogen, mass from periodic table. How do I go from moles to moles of this? My conversion factor is right here. Nothing is written means 1 and 1. So 1 mole of LiOH produces 1 mole of LiHCO3. Next, I go from mole to grams again. So molar mass again. 1 mole of LiHCO3 is how many grams? Plug it into your calculator. 1 lithium, 1 hydrogen, 1 carbon, 3 oxygen. Okay, so the total mass what I have comes out to 142 grams. Okay, that is the molar mass. Now, sorry, 1 mole is 67.96 grams. I've had 67.96 grams. Now you have your map complete. You start with this 50.0 grams LiOH multiply 23.95 grams 1 mole LiOH. Sorry, I should have kept some space. Multiply with the next that comes from here 1 mole LiOH 1 mole LiHCO3 multiply mole go on gram go on. 1 mole of LiH 1 mole of LiHCO3 67.96 grams of LiHCO3 mole gone. If you solve this, you would get the final answer as 142 grams of LiHCO3. Now what is this? This is what I solved quantitatively, meaning in theory. So this is my theoretical yield. So now I have theoretical, I have actual, plug that into the formula. Actual yield is 72.8 divided by theoretical, which is this, times 100. Like this, 72.8, 142. Get your answer. Your final answer is 51.3 percentage. The last type of question you can get from this concept is basically combining everything together. Okay, so we'll try to do this a little faster. Suppose that 12 grams of CO2 react with 8 grams of water to give 7.5 grams of C6H12O6. Determine the percent yield of glucose from this reaction. This, by the way, is glucose, C6H12O6. So question is asking what is the percent yield, and what's given to us is if you have 12.0 grams of this and 8.00 grams of this, and you ended up making 7.5 grams of this. So I made 7.50 grams of this. How much is the percent yield? Again, percent yield, let me write it here. Percent yield means actual over theoretical times 100. Actual is given to you, so this is my actual yield. I need theoretical yield. Now how do I find theoretical yield? Meaning how much product is made. Now again, this is basically like previous questions. Amount of reactant 1 is given, reactant 2 is given. The question is how much of this will you end up making, which means it is a limiting reactant question. I'll have to first go from this to this, then from this to this. Okay, again, because these are grams, I'll convert grams to moles first, moles of CO2, then moles of CO2 to moles of C6H12O6, and then moles to grams. My mole to mole ratio is 6 moles of this, 1 mole of this, 6 moles of this, 1 mole of this. Okay, so we'll apply the same concept. I'll just you over this answer. You start with what's given, grams of CO2. We are converting grams of CO2 to moles of CO2 using molar mass. So grams and grams gone. This is molar mass of CO2, 1 carbon, 2 oxygen. Now you have moles of CO2. Now I convert it to moles of C6H12, 1 mole of this, 6 moles of this gives you 1 mole of glucose. So mole of CO2, mole of CO2 gone. Now I have moles of C6H12. The question is asking grams of this. So I need molar mass of this. How would you find molar mass of this? 6 carbons, so 6 times 12.01. 12 hydrogen, so 12 times 1.008 plus 6 oxygen, so 6 times 16.00. When you plug this in, it would give you 180.16 grams. And that's what the molar mass is. So mole and mole gone, you're left with grams of glucose. Similarly, we do this with water. Grams, grams gone, mole, mole gone, mole, mole gone. You're left with grams of glucose. This on solving gives you 13.3 grams. So if I have these many grams, whoever gives me least is my product. Who gives me least is CO2, and what is it? 8.19, which means this is my theoretical yield. Now I plug this into the formula. Actual was given to me in question, 7.5 divided by 8.19. Theory, which I found by calculation, your final answer is 91.6%. So this is kind of like the biggest question that you can get, where you have everything given to you and you just have to solve for the percent yield. Again, there are no shortcuts. You will have to convert each of your reactant and figure out how much product each gives you using this approach. Okay, whichever is the least is your theoretical yield, and then plug that into the percent yield formula, and that's basically it.